Hi, all. So it's really going to be a very brief review, and I will skim a lot even over the topics that I have in the slides. So, so maybe as just preliminary note is that what was coming before Anderson model. So people were thinking about the metals described by a perfect crystal, but of course, dynamically it gives wrong behaviors. Instead of transport exponent beta equal to 1, it gives so which is diffusional behavior. It gives beta equal to 2, which is ballistic motion. And so one way to get diffusion is to introduce some kind of relaxation mechanism to description of the metal. But of course, it would never give you insulators. So in other words, you cannot mimic behavior of metal insulator transition by this way. And just a quick reminder, so what I mean by this simple transport exponents, so you just consider time evolution of the initial wave packet, which I will assume is localized at origin. It's not terribly important. And so you evolve it according to Schrödinger equation, so that's physical evolution. And then you consider expectation of the second moment of this operator. And by the way, for most of the talk, I will consider space L2 of CD. So just a discrete lattice, so think about tight bundling approximation. So this function typically would behave like T in some power beta, and if beta is equal to 0, so in physical language, you would say that you have mobility gap beta equal to 1 corresponds to diffusion, and beta equal to 2 correspond to ballistic motion. And all other values usually referred to as anomalies. Okay, so along comes Phil Anderson, and he made the proposal that actually there is this magic object by randomizing your periodic Schrödinger operator, you actually kill 2 birds in 1 stone. So you're going to see behavior which is actually compatible with metal insulator transition. So he just basically said, well, let's consider not the perfect crystal, but let's introduce some impurities by adding a random potential to the model. So really, H0 can be thought of for some purposes as just Laplacian, graph Laplacian on ZD. And this random potential has 2 parameters. So one is the strength of the disorder lambda, and you modulate the randomness by just saying that it's a multiplication operator by a random variable. And for simplicity, let's assume that it's IIT and has some joint probability distribution mu. So Anderson gave a physically compelling argument why it is a good model for metal insulator transition. But let me stress that his argument is probably compelling if you consider a long time behavior and dynamical behavior, but he sort of intuited from that this behavior for the model should be sustained for all times. And using some perturbative approach as well as classical analogy to random walk, posited that in dimension greater or equal than 3, you should expect diffusional behavior. And in addition, the sample exhibits the phase transition, so you would have both extended and localized states. For this model, dimension 2 is a critical dimension where you still don't expect phase transition, whatever it means, but at least you're not supposed to see extended states there. And dimension 1 corresponds to complete localization with uniform bounds on localization length. So in retrospect, his sort of rationale is clear. you start with two operators that has very different behavior. So one is free Laplacian, which exhibits ballistic motion, and second is multiplication operator, which of course corresponds, whose dynamics is just completely perfectly localized dynamics. And randomize the omega should break symmetries of H naught, and therefore changing its dynamical behavior. So, and of course, it makes sense to make them compete and interpolate between two operators. So it's plausible argument that for at least for large lambda in dimension 1, what you get is going to be localization. But in general dimensional case and the complementary statement of Anderson that no matter how small lambda is, you will see diffusion far less intuitive even on the physical level. So in fact, delocalization and critical behavior were not satisfactory studied with this original work, even from the physics perspective. And it took physicists some 20 years before they were more satisfied with these arguments. And so in particular, there is so-called scaling argument, which goes back to gang of 4, and other ideas like effective field description, which is called nonlinear sigma model, etc. So let me, in one slide, just flash previous sort of pioneering work on localization. So first, probably the first result that is really about localization was due to Goldscheidt, Molchanov, and Pastur in '77, and they considered a very special one-dimensional continuous random Schrödinger operator. And in higher dimension, method that was first introduced by Frisch and Spencer, called multi-scale analysis, was inspired by KM construction. I will explain, hopefully, why KM enters into the game. I mean, this basically that controls the small denominators. And in 10 years after that, Eisenman and Molchanov introduced an alternative method of proof known as fractional moment method. If time permits, I will comment why actually they wanted to consider an alternative method. And finally, about the same time, Eisenman came up with the idea how to prove dynamical localization. He introduced this concept of eigenfunction correlator. Okay, so what specifically I mean by localization? So again, I will consider just operators on ZD for simplicity, and so for a given configuration omega, I will say that interval is a mobility gap if two things occur. So first of all, it should be spectral localization. So the spectrum in this interval is pure point. But the second condition is what I call here condition 1, is basically conditions that the corresponding eigenvectors are exponentially localized. So they have what is called a localization center, each one of them, and they decay exponentially away from this localization center, but not uniformly. So there is some kind of mass xm here in front of this exponential decay. And in fact, you cannot get rid of this factor. So this looks much stronger statement than the one which was proposed by, say, Anderson. So in other words, beta equal to 0 is much weaker statement, but actually it's all or nothing usually. So if you cannot prove exponential decays, then you cannot prove anything at all. And it has to do with the fact that localization actually is sort of finite volume criterion, in a sense that I'm going to explain. Okay, so let me just, again, so Christian has this beautiful 2 lectures on YouTube that you can listen to, view. So let me just give very sort of rudimentary picture here, right? So, so consider a cover of ZD by boxes of finite size, so capital L. And I want them to overlap for reasons which will be clear in a moment. Okay? And now assume hypothetically that this condition 1, this exponential localization condition, holds not for the full operator on ZD, but on operators restricted to the boxes lambda LA, so which are depicted here, without polynomial prefactors, so with uniform. So actually, it cannot happen, but it doesn't really matter. Okay. So assume that it is true. And then the question is, can you just from this information obtain that same exponential localization actually holds for the whole ZD, or at least for any box of size which is much bigger than the original box. So why it is so, at the beginning, maybe it looks a little bit crazy, but if you think a little bit about this problem, then you realize that it's not so particularly crazy. So why? Because if you take eigenfunction for one of the small boxes, so pick some localization center which is deep inside the box, so corresponding eigenfunction look like something like this bump that I depicted here. And then you see that, in fact, it's not difficult to argue that because it's sort of exponentially small at the boundary of this box, and in fact, it's going to be an approximate eigenvector for operator on the whole ZD. Again, so it's not an eigenvector, but it's an approximate eigenvector, right? So then the idea is you sort of start to look at all those boxes, take them together, and construct an overcomplete basis for L2 of ZD, which consists of eigenvectors of this type. So by selecting some of them and throwing some other ways, you construct non-orthonormal basis for L2 ZD, but which has this almost orthonormality property, right? So that has to do with this exponential localization, right? So the question is, so of course you can normalize it, but can you orthonormalize this basis in such ways that a new basis is very close to the original one, right? So then it's sort of the first step in diagonalization of the Hamiltonian, right? So you think a little bit about that and you realize that it's not that easy, right? And why it is not so easy, it's easier to just to construct an example where you see that things can go badly. So you take a random system on a box lambda L and just extend it periodically to the whole ZD, right? Then you see that, well, it's a periodic system, right? So of course, on each scale lambda L, so if you take any box of size lambda L, you see a random system. But if you look globally, it's a periodic system, and in particular, its spectrum is absolutely continuous, right? So it means that this construction of orthonormal basis is probably not such a great idea for such system, right? So what is missing here is, and actually was missing also in the physics picture, is this control of small denominator. So when you do this periodic extension, then you create eigenstates of small systems that has exactly the same energies, right? And so because of that, you have tunneling effect. So that's what destroys actually localization if you do it periodically. So the idea is to control this resonances, the energies which are very close to each other. And the tool that I'm going to use is called Wegner estimate. So interestingly, Wegner, of course, was a physicist, and but I don't think he realized that his estimate can be used that way. So what is the typical result of this kind? So you consider distribution mu, which is alpha Hölder regular, and then you can control probability of omegas for which interval I of energies contains at least one eigenvalue. And this probability is proportional to the volume of the box on which you work, and I raised in the same alpha power that is Hölder regularity. Okay? So it's turned out that this is more than sufficient to resolve small denominator problem. And in fact, with a little bit of work, you actually also can conclude that this exponential localization holds almost surely on ZD. I mean, it's a bit more delicate than that, but essentially that's what's going to happen. So one way or another, Wegner estimate plays an important role in all approaches to localization. So I mentioned multi-scale analysis and fractional moment method. So fractional moment method doesn't enter sort of explicitly into the game, but sorry, Wegner estimate doesn't enter directly in the fractional moment method, but it does play a role there. But more importantly, it shows that it suffices to establish localization on finite system instead of infinite volume one. So this usually referred as finite volume criteria. And unfortunately, and that's what makes diffusion, delocalization so hard, is that we simply don't have a finite volume criteria for this. Okay, so very briefly, let me say a few open problems in this business. So natural question, what you do when your distribution is actually singular, right? So natural model for this metal insulator transition would be the one where you just decide, you flip a coin and decide whether you put the, say, impurity on an ion in your lattice or not, right? So that means that natural distribution in this problem actually Bernoulli distribution, right? And so in dimension one, it sort of can be covered with a little bit more work, but fairly straightforwardly. But in dimension greater than one, new ideas are needed, and first result of this kind goes back to Borgan and Koenig, who showed that it's possible to obtain localization near the bottom of the spectrum, and the idea that is heavily used there is a unique continuation principle and to control probability Sperner's law. Now, the discrete case is even trickier, because, as we know, the unique continuation principle as it is doesn't hold for lattices. I mean, eigenfunction can be supported on a finite set, right? And then, inspired by some work in harmonic analysis, Ding and Smart and Li Zhang later overcame this difficulty in dimension 2 and higher. But this proves work only at the bottom of the spectrum, which is maybe okay, but what is important is they only work in weak disorder regime. So lambda, just to remind you, it's the strength of the disorder, so it has to be much smaller than 1. So showing that localization persists for all lambda, and you have full localization for large lambda remains an open problem in the field. Now, again, very briefly, what we can say about delocalization, not much. And the result that is sort of, at least sort of from formal point of view, is close to what probably Anderson envisioned. It goes back to Erdős and Young with extension with 3-author paper where they added Zamhofer. So it's a weak scaling limits for dynamics of H omega. So the idea here is that you want to consider a case when lambda goes to 0, but you want to look at long time behavior for this model, and that's what the scaling limit is. And you sort of look at the mean free path for this model. You see that it is given, roughly speaking, is 1 over lambda squared. So the first interesting scale when you start to see collisions is C over lambda squared. And that's what they studied, and they obtain in this scaling limit, you get Boltzmann equation. Of course, it's also interesting what happens if you have not just 1 or 2 collisions, but many. And they pushed this further with Zamhofer and managed to go to an inverse power of 2 plus delta for lambda for time t. And just to give you an idea how delta is, it's just 1 over 6 in dimension 3 if memory serves. And on this scale, you start to see quantum diffusion. So this problem, as I mentioned, is probably most directly related to original Anderson work and utilizes diagrammatic technique and the renormalization approach. But let me stress that this is clearly limited. I mean, all these ideas are perturbative, and the complexity, of course, increases very fast just by pushing exponent from 2 to 2 plus delta. So main difficulty in this approach is control of the memory term. So once you start to expand exponential into some expansion, then eventually you have this last term left, which is the memory term, and it's control which actually spoils everything. So, and at least from my perspective, this control of memory term is effectively removed when you use this scaling argument of gang of 4 on a linear sigma model. So that's, in particular, it's sort of, for me, it's main reason why you actually see diffusion if you use those methods. Okay, so I will probably sketch the Spencer program altogether. So just maybe one word about this. So what I draw here is sort of schematics for a phase diagram for H omega in dimension greater than 1. So in blue, it's a spectrum of unperturbed operators, think Laplacian. And then as you start to increase value of lambda here, so the horizontal direction is energy and vertical is lambda, the strength of disorder. So as you start to increase lambda, you see the emergence of this red region, which is localized region. And we don't know what's happening here. So physicists expect that you would have extended states there. Right? So Spencer program, roughly speaking, was the idea of you want to look at what happens at the mobility H. So let's say if inside here is extended states, you want to understand what happens at the mobility H. And the idea of Spencer was try to approach this from outside and see how localization length diverges. So you're still in the localization regime, but you want to understand how localization length diverges when you approach Easter. So let me skip the rest of this part. And again, very briefly, just wanted to mention that sort of natural way how you can get the delocalization is to avoid coherence, and coherence often comes in presence of loops that we have a lot in ZD. So the natural object to consider is on showing operators on regular tree graphs. And indeed, Klein in 94 showed a C spectrum for beta lattice in the weak disorder. And it was, the theory was later developed further by a number of different groups. And but probably the most complete picture is by now established by Eisenman and Warzel, who I also identified sort of a new mechanism leading to delocalization, which is called resonant hybridization. So that's also a concept that will play a role in what I'm going to say about linear response. And but let me note that you don't get a spectrum which is so you do get a C spectrum, but it's of ballistic. So spectral data correspond to the ballistic motion rather than the diffusion. Okay. So unfortunately, I would have to skip altogether critical dimension 2. And as well as eigenvalue statistics, because I'm running out of time, as well as models with interaction. So let me just say a few words about linear response, which is a little bit sort of tangential to what I was saying up to now. Well, not completely, but so that's a report on work in progress that I'm involved with Wojciech Derok and Martin Frass. So you want to consider a time-dependent Miltonian. So you have some operators. Think about the Anderson model. In fact, you want to look, allow for magnetic fields there to make it interesting. But And then, apologize, beta here is not going to be transport exponent, it's just going to be driving strength, and W of t is your driving. And you consider a finite box of size script to L, and you are trying to understand the linear response for this situation. So you start with some unperturbed density matrix, which is, so I apologize. So I assume that W times D0 is 0, right? So then you start with unperturbed density matrix, which is commuting with Hamiltonian at time 0, and then you evolve it in time according to Heisenberg picture. And then in the first order in beta, you get this linear response formula that appears, that I have written here. So it plays important role in many applications. In particular, from our perspective, the most important application that we wanted to look at was Green-Kuba formula that sort of explains quantum Hall effect, and we wanted to understand whether it's justified or not. So the question really is why this beautiful formula works in practice. So this object rho, this perturbed density, depends on 3 parameters. It depends on strength of the driving beta, time t, and system size L. So if you want to probe response reasonably well, you need to consider a thermodynamic limit L goes to infinity first. And second, if you want this response to be non-trivial, you need this product of t and beta to be at least of order 1 and preferably actually go to infinity. So when I said that something is of order beta squared, this completely ignores both L and t dependent. So why is this linear response theory is actually applicable in such regimes, right? So and we know that they should be, because they describe quantum Hall effect quite nicely. And so Green-Kuba formula for quantum Hall effect is this can be written in different ways. Well, so here's this one, I hope, familiar formulation of that. So this is it's conductance of Hall conductance, and it looks like this trace of this double commutator. So P here is the Fermi projection for operator H omega, let's say, or H naught. And lambda 1 and lambda 2 are so-called switch functions. So that's function that takes value 0 in one direction and 1 in the second direction. No, sorry, it takes value 0 when x is negative and takes value 1 when x is positive in, say, x in first direction, if lambda 1, and lambda 2 takes sort of is a switch in this y direction. So we know quite a bit about this. This was studied since Belisard and Schutz-Baldes, for instance, and on algebraic side and on analytic side by Avron, Zahler, Simon, and Eisenman, Graf, etc. Right. So it is well-studied object, and sort of this formula makes sense as long as Fermi projection decays sufficiently fast. So the kernel of Fermi projection has to decay. In particular, it works perfectly well when your Fermi energy falls into the mobility gap. But if you want to justify this formula from sort of quote-unquote first principles, then we know how to do it when you have a gap condition. But when you don't have a gap condition, then when you have, for instance, a mobility gap, then it was pretty much open problem if you take limits in the right order. And this mobility gaps are important because if you just impose gap conditions, then you actually destroy plateaus. So it's not going to give you a right picture. Right? And using adiabatic framework, you sort of assume that dependence on time is small, and then you start to develop a theory that for this case, and this theory works well, as I mentioned in the gap case, because dynamical evolution follows the spectral one, in this case. So in particular, if you start with spectral projection to the spectral data that is isolated from the rest of the spectrum for all times, then its evolution is close to this spectral evolution. But it's turned out that it's not going to be very useful in our setting because of the, so I would have to skip all of that. So because of the hybridization phenomenon. So problem is that once you start to derive system, then you start to see that eigenfunctions hybridize. So in other words, you start with localized system, but it's after you derive beta, you lose this feature, and eventually you start to see sort of local delocalization. So in particular, it leads to the following interesting question, and that's going to be my last slide. So spectral flow of eigenfunction for this time-dependent problem are, this flow is very non-local because of this hybridization phenomenon, even for finite system, and in fact it's discontinuous for infinite system. So, so Folk adiabatic theorem suggests that dynamics should follow spectral data, right? So, but on the other hand, it's extremely non-local, and if you want, sort of physical intuition tells you that if you started with a localized system, maybe it should remain localized. And the question is who wins, right? So localization versus adiabaticity. And it turned out that the localization essentially is the winner, at least in physically interesting regime. And result of this competition is actually not adiabatic theorem, but locobatic theorem, which informally can be formulated as the following result. The physical evolution follows the local spectral data, not the global spectral data. So I'm out of time, so let me stop here. Thank you.